Hey everybody, welcome to our, let's see, what test is this? Energy. It's our energy test review. I know we just got back from Thanksgiving break, so there's probably a lot of questions that you have. I hope that the practice or the review that we did in class helped you guys maybe spark some questions. If you have any specific questions, go ahead and type those into the chat, and I will kind of work a few things out here and there as we go, add in a few tips of my own. Could you explain problem 1, questions D, E, F, and G? So Mia, I just sent out the key a little earlier with the key in the rubric to problems 1, and you're talking about the test review, right? Not the practice test, but the test review itself. Yes, okay. So what Mia's talking about is this page right here, and it has the test review with the graphs, and then it wants you to make a diagram and explain what's going on. Okay, so specifically you want to look at D, E, F, and G. So D, let's see, D shows us, all of these are showing us energy bar charts. And so in the first energy bar chart, we have, let's say, 3 bars. And those should be equal. It has 3 bars of kinetic energy, and then that's at position 1. And then at position 2, it's going to have 3 bars of gravitational potential energy. And again, just 3 bars. So what we want is a diagram, a picture of something that could explain this. And then we also want a description of what's actually going on at location 1 and location 2. So we have to think of a situation where we have all kinetic energy being converted into all gravitational potential energy. So this would be my before, this would be my after, position 1, position 2. And so the very simple example we can give here is the swinging of a pendulum. A pendulum is basically just a bob on a string. So this is some type of mass hanging on the string, and if I pull that mass up here and let go, it's going to fall and it's going to start swinging back and forth. And as it swings back and forth, it's going to convert gravitational potential energy to kinetic energy and then back to gravitational potential energy. So in this example, my diagram would probably look something like this. I have my string, let's see, we have kinetic and then gravitational. So kinetic energy is the greatest, and there's no gravitational potential in position 1. So position 1 would be the bob straight down. So there's position 1. Position 2, and what I'm assuming here is that prior to position 1, it was held up and released. As it passes by position 1, it has all kinetic energy and no gravitational potential energy, and that is if I set this height that it's at right now as 0. Well, we know it was released up here. It's going to fall down, follow that arc, and because of its own inertia, it's going to continue on, and it's going to swing up. It's going to swing up here. So then I'm going to have the bob and the string here, and this would be position 2, where at that moment, for a brief second, it's going to stop and then start swinging back the other way. And so that's why I have only gravitational potential energy at position 2, and I have all kinetic energy at position 1. So that is graph D. So this was number 1 on the review, letter D. If we look at E, in E we have all spring potential energy, and then it is converted into kinetic energy. And I'll go ahead and draw that. So we have all spring, 3 bars again, spring potential energy, and that is converted into all kinetic energy. This is position 1, this is position 2. right? In this one, it says an object oscillates horizontally. Oh, let me turn my notifications off here real quick. Oops. There we go. Okay. So in number 2, it says an object oscillates horizontally at the end of a spring. So in this situation, what we would have in my diagram, what I would draw in my box here, is, let's say I had a table and I had a spring here and I had some type of object that was compressing that spring. And when it was compressed before, why is it still doing that? Do not disturb should be on. Okay. While it was compressed, it should have only spring potential energy. And then once it's released, so position 2, let me coil that spring up a little bit more. So it's really compressed, so that would be position 1. And position 2 is going to be somewhere over here where all of that spring potential energy has been converted into kinetic energy. Ethan says, okay, let me start back with Mia. Mia says, could a ball being thrown upward be a correct example? Absolutely, Mia. That would be perfect. As long as, let's say, the person that throws the ball up at their hand, if that is our 0 reference point for gravitational potential energy. Yes, it would start with all kinetic and end with all potential. That's exactly right, Mia. And with these examples here, certainly there's going to be more than one case most of the time where you can follow this type of energy conversion. Ethan says, okay, so let's say I had an object that had 300 joules of gravitational potential energy, and then all of that energy was converted into 300 joules kinetic energy. Was work done? If so, how much? Before today, I would have said no work, but after reading the test review, I think 300 joules of work was done. Okay. So here's the answer to that, Ethan. So you started with gravitational potential energy, you ended with kinetic energy, and we would say that mechanical energy was conserved. Mechanical energy was conserved. When mechanical energy is conserved, that means a conservative force is acting on the object. And what a conservative force is a force that does work on an object. And path does not matter. And the example I gave in class to you guys is when I lift something up into the air, it doesn't matter how that object got to that specific point. If I lift an object up to, let's say, 10 meters into the air, its gravitational potential energy is going to be mgh. It doesn't matter how it got to that height of 10 meters. Its gravitational potential energy will always be mgh. And because it doesn't matter how it got there, we say that that is a conservative force. But in this example, what is the force for gravitational potential energy? Well, remember, energy, work, is a form of energy. So if I'm looking at this gravitational potential energy in terms of work, and work is force times distance, the force that's being applied here is that mg. What force is mg? Well, that's the gravitational force. That's the gravitational force. So because it's conservative, we can use this conservation of energy equation. It makes our life much easier, or it makes the math a lot easier. So what's doing work in this sense, Ethan, is gravity. But we don't write it as work in this instance because it is a conservative force. If it had been work done by friction or an applied force or some type of work done outside of my system, then I would have written that as work, right? But let's say that they ask you, well, how much work did it take to get to that position if I lifted it up? Well, we know that work is always going to be equal to the change in energy. So if you have a change in the total amount of energy, then work was done. Here, I didn't have a change in the total amount of energy because this was 300 joules and this was 300 joules. And so I agree with you, Ethan. I wouldn't say that work was done in this instance. I would say that the mechanical energy was conserved, and it was just transformed from one type to the next. But if we really get specific about it and we talk about gravity doing work, then and taking the earth out of my system, then I could look at it that way, that work was done. Okay? So I hope that helps answer your question. I'm not sure which question threw you off. Was it question on the test review? Was it question 7 on the practice test that threw you off? Maybe he'll answer me. In the meantime, Mia says difference between total energy and mechanical energy. Okay, so mechanical energy is only gravitational potential, spring potential, and kinetic. That's it. All right? That's it. Friction, applied forces, when those do work, tension forces, normal forces, when those do work, those are not mechanical energy. Okay? It's taking away thermal energy, all sound energy, light energy, all of those are not types of mechanical energy. These are the only types of mechanical energy. So the very first day, what did I do? I dropped that basketball, that little rubber basketball in class, and that little rubber basketball fell to the ground, and then it bounced up, and then it bounced up, and then it just kept bouncing until it no longer had any height. So what's happening each time this ball comes to a new height? What am I seeing here? I'm seeing a decrease in the gravitational potential energy. Well, gravitational potential energy is a type of mechanical energy. So my mechanical energy is decreasing in this instance. So we cannot say in this ball bouncing and then coming to rest to a stop, we cannot say mechanical energy was conserved. But what we can say is that total energy was conserved. How do we know that total energy is conserved? Because that's the first law of thermodynamics, is the conservation of energy. If the gravitational potential energy decreased, then energy elsewhere, it had to be transformed into something else. It had to go into something else. And in this case, we talked about when that ball hits the ground, those molecules begin to vibrate and move around. And whenever things are moving around, it creates heat. So yes, the mechanical energy, the energy of its motion and the energy of its position, that decreased, but that energy was transformed into the floor as heat. So total energy was conserved, but mechanical energy was not. So there is definitely a difference between mechanical energy and total energy. Abby says, if you haven't already, can you do 4 on the very last page? 4 on the very last page of the test review. Number 4. I don't see a number 4. I'm sorry, Evie, I'm not seeing a number 4. Do you mean on the practice test? In the packet, okay. Alyssa says, will we ever have to take Earth out of the system on the test? What you need to be careful for on the test is when it says work done on, the system, or work done by, let's say, in this case, gravity. We talked about this one in class too. If I'm a person, and I'm happy today, if I'm a person and I have a ball and I raise that ball up into the air, I've given it more energy. Well, where'd that energy come from? Well, it came from the energy from the work that I did on it. So I would say if this was my zero reference frame, I would say it started with no energy and now it has gravitational potential energy. Where that energy came from? It came from the work that I did on it. Now, why did I do positive work on that ball? Because anytime we do positive work, this is important, anytime we do positive work, then the energy of that object has to increase. When I do negative work, the energy on that object must decrease. So in this case, it gained potential energy, so that means I did positive work on the ball. Okay? Now, what about the work done by gravity? The work done by gravity. Well, where does gravity want this ball to go? Gravity wants this ball to go whoop, right down there. And the force of gravity is what direction? Down. That weight force is down. And what did we learn about when the direction of the force and the direction of the displacement or the distance that that object moves, when they're in the same direction, there is no, so F parallel D equals work. When they're in the same direction, there is no angle. There is no theta. And cosine of 0 is 1. So it just becomes work equals force times distance. So the work done by gravity is the force of gravity times the distance that it was displaced. And that's how we get the work done by gravity equal to mgh. Now let's do the reverse. If I lift that ball up, well, now this force is going in the opposite direction that gravity wants it to go. Gravity is pulling it down and the ball went up. They're in complete opposite directions. If I draw that red arrow here, what is the angle between those two? It's 180 degrees. So in this case, the cosine of 180 degrees is -1. So the work done by gravity when you lift the object is negative. The work done by gravity, so when lifting an object, the work that I do to lift it increases the energy of that ball. Therefore, I did positive work on that ball. But if I say, well, what was the work done by gravity? That would be, let's see, this work was positive. The work done by gravity, in this case, would be negative. So, Alyssa, you're never going to have to remove Earth from your system specifically, but you might get caught in something like this. The work done on the system by me was positive, but the work done by gravity was negative. Okay? Let's see what we have here. Ethan says, on the front of the test review, it said work was done if energy went from potential to kinetic, if energy transferred. That's what threw me off. Shout out to James. Okay. Evie says test review. Oh wait, that's on the packet. So Evie wants to look at packet and number 4. Number 4 on the last page of the packet. All right, Evie, this is a great question for us to go over. You will definitely have a couple of these, at least 2 or 3 of these types of questions on the test. So this is a really good skill to know and understand. It says a car is traveling, so this is number 4 on last page of packet. It says a car is traveling at a velocity v. So we have a car, vroom, vroom, and it's moving along at a velocity v. A car traveling at a velocity v can stop in a minimum distance of d. Okay, so if it's moving with a certain velocity, we know that it can come to a complete stop. So we'll say at rest here, at a certain distance, boom, d. What would be the car's minimum stopping distance if it were traveling at a velocity twice that much? So actually this should be d, right? From the front of the car to the front of the car. Come on, Zamzo. Now they're giving us a second scenario. It's the same car, even though mine looks much bigger here. It's actually the same car, in case you didn't know. And it's traveling twice as fast. Now we want to know, at what d can it stop at? 2d? Half d? 4d? How in the world am I going to figure this out? This is a strategy you will need to use over and over and over again. All right, so get used to it. What's the equation that is going to relate velocity and distance? And what test are we in? We're in the energy test, right? So we need to be thinking energy. And even when you take the AP test, 9 times out of 10, you want to think in terms of energy because it's easier math. So if I'm thinking in terms of energy, I'm going to go, okay, what type of energy does the car have before? What type of energy does the car have after? And I say, well, initially it is moving, and energy of motion is kinetic energy. And at the end, at position 2, so if I labeled this position 1 and 2, this would be position 1, this would be position 2. At position 1, it has kinetic energy. At position 2, it has no energy. Scratch our head and wonder, we can't go from all energy to no energy. So what happened here? And this is where some of you may think about that LOL diagram and you go, oh, I have 4 bars of kinetic energy. Now I have none over here. Well, what happened? That means that that energy had to leave the system. How much energy had to leave the system? 4 bars of energy had to leave the system. How do we decrease the energy of a system? How do we change the energy inside of a system? We do work. Now, would this be positive work or negative work if I'm decreasing the amount of energy it had? Decreasing energy means negative work. Okay? So we would say that the kinetic energy is equal to the negative work done on the object, because we have to remove that amount of energy there, yeah? So in the end, it equals, or actually, sorry, K minus W equals 0. Hello, Zamzo. Can't have negative kinetic energy. So when I move W to the other side, we see that kinetic energy equals the amount of work that was done. Well, what's the equation for kinetic energy? Here we go. 1/2 mv squared. What's the equation for work? We just said that that was force times distance, yeah? So now do I have the variables I'm relating in this problem? Velocity and distance. So what I'm going to do now is a proportionality. In both of these problems, they both had the same mass. The car had the same mass. So that's irrelevant to the comparison between these two scenarios. If I apply the same force, what can be its minimum stopping distance? It's the same car. I'm able to apply the same amount of force to those brakes. The 1/2 isn't changing, so here's my proportionality. If I change the velocity, it is proportional to the change in the distance. Well, the velocity squared is proportional to the change in distance. Why can I just ignore these other things? Because they're not changing from this example. We'll say from scenario A to scenario B. Those things aren't changing, so I can ignore them. But instead of writing an equal sign between here, I write a proportionality sign because v squared is not equal to d, but it is certainly proportional to d. So here's the trick. You can plug in any numbers you want, but the easiest numbers to plug in is the number 1. So if in the first scenario I had a velocity that was equal to 1, I'm going to plug in a 1 here, and I'm going to square that 1. What would my d be? Well, what is 1 squared? 1 squared is equal to 1. So if v was 1, d was 1. Okay, stay with me. You don't have to do that step every time, but I'm just proving a point. Next, they say that we double the velocity. So I multiplied this v times 2. So now, if I come in here and say, I'm going to double that velocity, instead of writing a 1 there, I'm going to write a 2 there, and I'm going to square it. And what is 2 squared? 2 squared is 4. Well, what was my original distance? It was 1. What's my new distance? 4. This is why I use 1 every time, because this math is so simple. 1 times what equals 4? 4. So if I double the velocity, I will quadruple the distance because of that squared function. If my proportionality, let's say for example, was mgh is equal to mgh is equal to a new mgh, or we could say 1/2 mv squared. If I wanted to talk about doubling the mass, what would that do to height? Or if I doubled the height, what would that do to the velocity? In another example where, let's say we get a proportionality that is directly proportional, let's go back to kinematics for a second. A equals v over t, so we could rearrange that and say v equals at. So here's a direct proportionality. If I were to double t, I'd have to have, if an acceleration remained the same, I'd have to have double the velocity, or 2 times the velocity. If I halved it, then I'd have to have half. But here we have this squared function, and so that's why it goes from 1 to 4, not 1 to 2. So that's the question on the last page of the packet. And that, to me, is a really important thing to know and understand. Okay. All right, let's talk about what's in the system for a moment. The example that we talked about on the quiz was we had a spring, we had a cart that was launched, and here was position 1, and then here was position 2. Now, energy before equals energy after, and most of the time, most of the problems we're looking at, mechanical energy will be conserved. Why? Because in AP Physics 1, they're really going to ask you questions about mechanical energy being conserved. They're only going to ask us questions using spring potential energy and gravitational potential energy and kinetic energy. They might talk about friction a little bit, but for the most part, they're only going to give you problems where mechanical energy is conserved, because we're dealing with conservative forces. And if I'm dealing with a conservative force, then it doesn't matter what happens in between those positions. All that matters is what happens here at this position and here. What is the state of energy at position 1? I have spring potential energy. What is the state of energy at position 2? Well, in this case, if friction was acting on it, then I would say, let me go ahead and add another bar there, because this was the one that was on the quiz, number 8 on the quiz. And I would have, let's say, 2 bars of gravitational potential energy and 1 bar of kinetic energy. And what goes in my system, I ask myself, what provided that spring potential energy for me? The spring. So if I'm considering that energy in my equation, then I have to put the spring in the system. What provided the gravitational potential energy? The earth. So if I'm considering gravitational potential energy, then I have to put the earth in my system. What gave it this kinetic energy? Well, kinetic energy is the energy of motion. What's moving? The cart is moving, so I have to put the cart in the system. But we were told that friction did work. That work. Friction did work on the cart, which means it slowed it down, which means that it's a non-conservative force and it reduced the total amount of mechanical energy. Look, I have 4 bars of mechanical energy here and I only have 3 bars of mechanical energy there. That total amount of energy decreased. What happens when I decrease the total amount of energy? I do negative work. Well, how did I get that energy out of the system? If I had 4 joules here and 3 joules here, that means that 1 joule was taken out. 1 bar of energy was removed. How do we remove energy from a system? We do negative work on that system. Friction, almost always, is going to decrease the amount of energy, unless you're talking about traction. But because it decreases the amount of energy, it does negative work on the system. That's where that extra little bar went. It didn't just disappear. It was lost due to friction and heat. That friction turned into heat. Now, what provided the friction? The track did. So guess where the track goes? The track goes outside of the system. I can't put the track in the system because how can the track remove energy from the system if it's in the system itself? An example I told some students today was, if you and I are in a room and you have 2 apples and I want to take one of those apples, I can take one from you, right? But if we're both still in the room, there's 2 apples still in the room. I have to go outside of the room with that apple to decrease the amount of apples in that room. That may or may not connect with you. But that's what I'm getting at here, is that in order to take this block of energy out of this system, because right now, before I had 4 blocks of energy in this system, and then afterwards I had 3 blocks of energy in that system. 1 block of energy was removed through friction. And because the track did that, it can't be in the system because it had to take it. The track had to take that energy away. All right, I hope that helped with that. Problem 2 on the test review is something that unfun going to be on the test. Problem 2 on the test review. Yeah, that's kind of like the unfun one we had last time, right? With all the variables. So you guys need to be getting good with that kind of stuff and making your graphs and doing your linearization and all that. But I will give you a hint. There will be no linearization on this test. So you don't have to worry about linearizing for this test. Question 9 on the practice test. It wasn't on the key for some reason. Yes, because I uploaded the key from last year, but I do have a new key that I'm going to scan in and send to you guys. So you said number 9? Number 9. A ball is bounced on the floor and does not return to its original height. So this is kind of like what we talked about before. Number 9 on the practice test. So we have a ball that is dropped and then it continually bounces and decreases, right? Which of the following statements is correct? A says mechanical and total energy is conserved. Mechanical energy in this example is not conserved. And how do you know that? Well, first off, you have to ask yourself, what are the types of mechanical energy? UG, US, and K. UG, US, and K. Did I start at this point? I started with a certain amount, let's just say 10 joules of gravitational potential energy. In the end, when it's at rest on the floor, how much energy does it have? It has 0 joules. It doesn't have any gravitational, it doesn't have any spring, it doesn't have any kinetic. So when we say that something's conserved, that means it has to be the same before as it is after. When would mechanical energy be conserved? If we looked at this point right here where it had 10 joules of gravitational potential energy, and then right before it hit the floor, we could say it had 10 joules of kinetic energy. And only that specific example would mechanical energy be conserved. As soon as it hits the floor, it's going to lose energy to that non-conservative force, and it's steadily going to decrease, 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 and lose energy to heat, friction, sound, all that. The moment it starts losing UG, US, or K, total UG, US, or K, mechanical energy isn't conserved. However, total energy is conserved. Because remember, total energy isn't just these 3 things. Total energy, you're talking about thermal energy, light energy, sound energy, chemical energy, geothermal energy. All those different types of energies add up to the total energy, and that energy will be conserved. Okay? The wording on problem 2 killed me inside. Not sure which number 2 you're talking about. There's a lot going on. Problem 13 on the last page of the unit packet. All right, let's pull that up. Unit packet. So this is a multiple choice one. Let's take a look at number 13 on the unit packet. You push a heavy crate down a ramp. So we got a ramp, also known as an inclined plane. So I'm pushing that crate down the ramp, so it's going that way, at a constant velocity. And we know that if it's at a constant velocity, then there's no acceleration, right? And if there's no acceleration, then the sum of all the forces is 0. So that keyword constant velocity tells us that the net force acting down the ramp is 0. So if I draw my free body diagram and look at what forces are acting on the box, well, I know that I'm pushing the box down. So from the center of mass, I'm pushing the box down. I have an applied force. I also know I have a weight force right there. I have a normal force perpendicular to the surface. And I have a frictional force. And the frictional force is going up the ramp this time because it's going to oppose the direction of motion, and we're pushing the object down the ramp. Well, gravity has a component that is that way and that way. So that component plus this applied force must equal that frictional force. So if I add up the vectors going up and down the ramp, the applied force plus the x component of the weight force have to equal that frictional force. Only 4 forces act on the crate. Which force does the greatest magnitude of work on the crate? Now remember, work is force times distance. These forces are all going to act over the same distance, so whichever one has the largest force does the most work. And I just showed us here that that frictional force has to be equal to the applied force plus the x component of that weight force. So we know that the frictional force has to do the greatest amount of work. Okay. Matthew says, why can you ignore the 1/2? Because the 1/2 was the same in both scenarios. In both of the scenarios, that the kinetic energy of the car was 1/2 mv squared. So the 1/2 wasn't changing from situation A to situation B. Evie says it doesn't change, yes. And for the life of me, I can't do problem 2 on the smaller packet. Not sure what the smaller packet is. I guess that's the test review. We're not going to worry too much about that one right now. Matthew says, does anyone know what the 1/2 even stands for? Yes, Matthew, we can derive that 1/2 whenever we look at the force versus distance. And let's say I have a variable force. What did we learn in class? That the area under this curve equals. The area under that curve, anybody? Anybody? It equals work. It equals the work done by that force, because there is a certain distance, right? But what's the area of that shape? The area of that shape is going to be 1/2 my force times my distance. Well, what is, if it's a spring, springs have variable forces, the force changes as that spring is applying force. It's going to be kx is going to be my force, and then the distance that it moves is the compression distance. That equals 1/2 kx squared. So the area, the 1/2 comes from that derivation similar to that. I believe it stands for 1/2, Matt. I double checked. No, really, I would have never guessed. Okay, dude. I get. Please explain number 7 on the practice test. All right, number 7 on the practice test. All right, 6 and 7 kind of go hand in hand with each other. So in number 6 on the practice test, it tells you that a rope exerts an upward force on a 20-kilogram crate. The crate starts from rest and accelerates upward 5 meters per second squared near the surface of the earth. So there's this crate. It is 20 kilograms. An upward force is applied on it, and it accelerates upwards. And that acceleration is 5 meters per second squared. And they want to know what the kinetic energy is when the height is equal to 4 meters. Again, we always want to look through our energy glasses first, especially if they're talking about energy to begin with. And a lot of times they don't even talk about energy, but you can still use energy. So what type of energy did it start with? It was rest on the ground, so it started with no energy. After, it ended up with, or while it was moving, it ended up with kinetic energy because it accelerated. So it ended up with a maximum kinetic energy at the top before it came to a stop, right? How did it get that kinetic energy? Through positive work, because it went from no energy to having energy, so positive work was done. So I know that the work done on lifting that crate had to be equal to the amount of kinetic energy gained. Well, okay, so I guess that's what question 7 was asking, was how much work was done. The amount of work done was equal to the kinetic energy gained. Well, number 6, we found the amount of kinetic energy that was gained. We had to do a little bit of kinematics using the 5 meters per second squared and the height of 4 meters using v squared equals v naught squared plus 2a delta x, and then v naught was 0. Then the velocity at the top of the path, if it moved 4 meters, it had acceleration of 5 meters per second squared. We see the velocity is the square root of 2 times a delta x. When we plug in 5 here and 4 here and take the square root of that. What is that? The square root of 40? And so that's 6.32 meters per second. Now that I know what the velocity is that it's moving upward with, I can figure out how much kinetic energy it has, because kinetic energy is 1/2 mv squared. And they did tell me the mass was 20 kilograms. So it's just 1/2 times 20 times 6.32 squared. That's the kinetic energy. Well, now that I know the kinetic energy, I know that to get that kinetic energy, it required positive work. How much positive work? Well, the same amount of energy that it gained. If it started with 0 energy and ended with 400 joules of kinetic energy, then how much work did I have to do to get it there? 400. And whenever we did the 1/2 mv squared, that actually came out to 399. So I'm not sure why one question has 400, the other one has 399. They really should both have been rounded up to 400. But the work done by the force to raise the crate 4 meters above the floor had to be equal to the kinetic energy that was gained. Because that's how it got the kinetic energy, was doing work. And all of that work went into the kinetic energy. Yeah? Will your total energy always be conserved? For our purposes, yes. The energy in the universe will always be conserved. Energy is never created nor destroyed. Now, if we start looking at systems being isolated, closed, or open, then that'll be a little bit different story. But as far as we're concerned right now, total energy is conserved. Doesn't total energy literally always have to be conserved? Yes. It's all about perspective too, Alyssa. It's all relative, as we were talking today. Connor, specifying between heat and thermal energy is important, right? Since thermal is average kinetic energy in the system. If you were in AP Physics 2 or AP Chemistry, then Connor, yes, that would be an important differentiation, to know that heat is the total amount of energy that those molecules have, and temperature is the amount of average kinetic energy. But if you're talking about thermal energy and heat, then those would be the same thing. Average kinetic energy is not the same thing as total thermal energy or total heat. But in this class, for this AP test, you don't have to make that distinction. They won't ask you anything about that. Question 2 on the practice test, I don't understand it. Mia, if we have time, we'll get there. Wouldn't UG be gained too? Whoa, Dees. Yes. Dees, you are right. Gravitational potential energy is gained too. So we have to fix this, don't we? I love it. We start with no energy, we end with kinetic energy, but because we raised it up to a certain height, and this is not horizontal, we also gain gravitational potential energy. Yeah. So what's the work done? The work done is the sum of both of those. I know the kinetic energy is 400 joules. What's the gravitational potential energy I gained? mgh. Do I know what the mass is? Yeah, it was 20, right? So 400 plus 20 times 10 times 4. Are we getting somewhere here? Work is equal to 400 plus 20 times 10 is 200 times 4, which is 400. Or instead of 10, let's use 9.8. Somebody do that math for me real quick. What's the 9.8 times 20 times 4? Do I have those numbers correct there? $11.80. Wait, how did Dees get $11.80? Dees, how did you get $11.80? $7.84. My mental math is off. So yeah, 1180 joules. Yes, look at that. Look at that. I love it. So let's make a correction on that one. The answer to number 7 is E. Look at that. You get to moving so fast and you miss a step. That's why it's important to take all the time possible for those multiple choice questions, yeah? The smallest little thing can throw you off. And guess what? They put 400 on there for us so that we could make that easy mistake. You just did number 6 and you go, oh, 400, and it's going to be 400. Yeah, this is number 7, Connor. No, it didn't, Alyssa. It said how much work was done by the force in raising the crate 4 meters above the floor. If it said how much work was done to give it the kinetic energy, then the 400 would have been correct. But it said in raising it, and in raising it, we also gave it gravitational potential energy. So yeah, very nice. Very, very nice. All right. That one is 1180. 1180. Somebody mentioned FRQ number 2. FRQ number 2. This is the one with some boxes and some springs. I just uploaded the key to that one, but I don't think I've shared it with you yet. So I will do that after the webinar for sure. Okay, sorry, I got a lot of papers here. So FRQ number 2 was kind of a longer one. Had parts A, B. Ay, ay, ay. Too many papers. A, B, D, A, B, C, D, and E. All right, it's almost 9 o'clock, so we're getting low on time here. What I'll do, so number 2 on the FRQ is an old FRQ on the AP Physics B test, and I have for you from the College Board the scoring guidelines that go with that question, and also the problem worked out by an example problem worked out by a student, I guess it looks like. And so I want you to look at that so that you can see how the College Board scores, what the scoring guidelines look, how you get points, how you don't get points. And that's a longer problem, and we're running short on time, so I'll just share that key with you guys. Let's look at 20 and 21 on the practice test real quick with the little bit of remaining time we have. Number 20, a car moves in a straight line. A varying net force is applied and the car's velocity time graph is plotted above. Which of the following statements are correct? Pick 2. So what they've given us is a velocity time graph. Going back to our kinematics days, the velocity time graph looks like this. It's 0, and then we have a slope, and then we have a horizontal section, and they give us the little dotted lines here. And this is time t equals 0, 2, 4, and 6 seconds. Which of the following statements are correct? And it says to pick 2. The acceleration is constant. How do I get acceleration from a velocity time graph? Remember, when they ask you a question and they give you a graph, there's one of 2 things you're going to do. You're either going to divide those variables or you're going to multiply those variables. And so now you have to ask yourself, if I multiply them, that's going to be area under the curve. And if I divide them, then that is going to be slope. Which one of these will give me acceleration? Change in velocity over time, or change in velocity times time? That's the one that's going to give you acceleration. So what I need to look for, and if you don't know that, look at your formula chart. Your formula chart has that formula on there. So I need to be looking at slope, and the slope is the acceleration. So here the acceleration is, or so here the slope is 0. Here I have a slope, not sure what it is because they didn't tell me what the y-axis was, but I have a positive slope, and here I have no slope. So is the acceleration constant? No, it's changing. So A is not correct. B says the car travels the farthest between times 4 and 6. We're talking about distance here, or displacement. If I take the units of meters per second and divide it by a second, then I get meters per second, which we all know is the unit for acceleration. If I take meters per second and multiply it by a second, those guys cancel out and I get meters. What is meters the unit for? Displacement, right? So what do I need to be looking at to get displacement? Area under the curve. So it says the car travels the farthest between times 4 and 6. So that would be the area here. Or option D says the car travels the farthest between 2 and 4. That would be the area here. Very obvious that this one is greater. So between 4 and 6 is the greater delta x. So B is correct. And so C must be correct too. And C says the acceleration is greatest between times 2 and 4. Absolutely. That's where we have a slope. That's where we have a slope with our acceleration. So this is where I have the greatest acceleration. Number 21, it says work is a scalar quantity. If something is scalar, that means what? That it only has a magnitude, but no direction. A vector has magnitude, I forgot my E there, and direction. Scalars don't have direction. So direction doesn't matter with scalars. And it's telling us that work is a scalar function. What were some other scalar functions we worked with? Speed, distance. Yeah? So vectors were, the vectors we worked with so far was a lot of things. Velocity, acceleration, force, but energy. Energy's not a vector. You either have it or you don't. It doesn't matter what direction I'm going. Either I'm gaining energy or I'm losing energy. So don't confuse this with, oh, well then I can't have negative work. No, I can have negative and positive work. If I decrease energy in the system, it's negative. If I increase energy in the system, it's positive. But that isn't direction. With velocity, if I was moving to the right, then that was a positive velocity. If I was moving to the left, that was negative velocity. It doesn't matter if I'm pushing a box this way or I'm pushing that box this way. If I push it and it now is gaining velocity, it's accelerating, then it's doing positive work. Doesn't matter what direction it's going. If it's increasing its energy, it's going to be positive work. So in this example, it wants to know when work would be negative, which indicates that energy was removed. A says gravity causes an object to fall. We already talked about that. When gravity causes an object to fall, the force of gravity is down, the direction it falls is down, and when the direction of the force applied in the motion that the object moves are in the same direction, then that's positive work. So when a ball falls to the ground, gravity does positive work on that ball. Friction causes an object to slow down. Keyword slow down. I lost energy whenever the object slowed down. And if I'm losing energy, then that's negative work. So B is definitely correct. C says a person lifts an object. We talked about this, right? If I am that person and I lift the ball from here to here, I did positive work on the ball, but gravity, the work done by gravity was negative, right? Work done by gravity was negative when I lifted that ball up because it went the opposite direction that gravity wanted it to go. It went 180 degrees in the opposite direction that the force was being applied, so it had to be negative work. So B and C are correct. And lastly, it says an inclined plane causes an object to roll down. An inclined plane causes an object to roll down. Well, if I put a ball on an inclined plane, why is the object rolling down? It's not because anybody's pushing it, it's because of gravity. And is it going